This is our very last type of problem, and honestly, it's totally identical to the common ion problems. It's just referred to as a buffered solution, and I wanted to use that terminology because it's something that's important and will show up when you're in biology, and it's just a good vocab word. It's one of the most important acid-base solutions. The most common, most important example is blood. A buffered solution such as blood has the ability to resist a change in pH. So by having both the acid and its salt there, it doesn't rapidly change in pH. A buffered solution is a weak acid and its salt, such as HF and NaF, or a weak base and its salt, such as ammonia and NH4Cl. And see, by being a salt, it has either one of these alkali metals or one of these halogens with it. And so there's absolutely nothing different that we have to do to solve this problem, but I thought it would be good for you to even see going through another problem again. So the pH of a solution that contains 0.250 molar formic acid and 0.1 molar sodium formate. So my major species are this formic acid and this sodium formate. We need to choose the species that can dominate the reaction. Okay, it's going to be our acid, okay, because we know that this sodium here isn't going to contribute to this problem. So it's going to be my HCOOH, which is going to make H plus HCOO minus. And again, I started skipping steps again, but we need to write our equilibrium expression. That's definitely something that we need to have here. So forms H plus HCOO minus over HCOOH. It says find the initial concentrations of all the species involved. So I have my two species. So I have my HCOOH with an initial concentration of 0.250 molar. And I have my HCOO minus, because I really don't need that Na anymore. I could write it as COOH. Notice it's the same thing. COOH is 1 carbon, 2 oxygens, and a hydrogen. 1 carbon, 2 oxygens, and a hydrogen. And that's 0.1 molar. Okay, so now I'm going to list my initial change and final concentrations, my ice chart. It's going to become H plus HCOO minus ice. I have 0.250 molar here, and I have 0.100 here. That's my initial concentrations. That is 0. We're going to shift always towards our 0. And then we have to go ahead and solve the problem, which I didn't really give you a good space to do. But we can go ahead and solve it right here. So 1.8 times 10 to the minus 4 is equal to x. 0.100 plus x, which I got from right here, over 0.250 minus x, which I got from right here. I'm going to multiply. I'm going to get rid of my x's. I'm going to multiply by 0.25. I'm going to divide by 0.1. And I'm going to have x is equal to 4.50 times 10 to the minus 4th molar. I'm going to check my 5% rule. I'm just going to check it by my initial acid concentration. And I get 1.25 times 10 to the minus 2 molar, which is greater than 4.50 times 10 to the minus 4th molar. So my 5% rule check is okay. And then finally, I need to do my H plus we already have. That's what X is. But my pH is equal to the negative log of 4.50 times 10 to the minus 4th. So pH is equal to 3.347, and then 4.50 times 10 to the minus 4 over 0.250 molar times 100. My percent dissociation gives me a 0.180% dissociation. Exactly the same as the last problem, just renamed it as a buffer solution, and it's good to go. I want to actually move on to the one that you have as a practice problem, because it's a basic problem, and I want to make sure you set it up correctly. So I'm not going to walk through the whole problem, but I'm just going to do the setup. We have ammonia, which we know is a weak base, and it's salt, ammonium. Again, we're not going to worry about that Cl because that's not going to be a part of it. List our major species. So we have NH3 and we have NH4 plus. We know that we have a Kb that's given to us, so we know this is going to be a Kb problem. So we know that our NH3 is going to dominate, but let's remember that when we have NH3, we need to remember to add H2O and form NH4 plus OH minus. Remember that this is going to be a liquid. It's not going to be a part of our problem, and that will end up with an initial concentration here of 0.30 molar. This isn't going to be part of anything, and this is going to be the 0.20 molar. So I'm getting that from here and here. From there, it's exactly the same problems that we've been doing, and I will leave it to you to go ahead and continue to solve that. But I wanted to get that equation down so that you can see how to get it started.